Hello, I'm Maximilian Merz and I'm going to present joint work with Christoph Bergholz. Our paper is concerned with probabilistic databases under updates, and we look at both Boolean query evaluation and ranked enumeration. So let me introduce our problem setting. We work on tuple-independent probabilistic databases. That means we have a probabilistic database where every tuple is an independent probabilistic event, and we store the probability alongside each tuple. We fix a finite domain, a finite set of constants, we fix a database schema, and we fix a first-order query phi, which may be either a Boolean or a non-Boolean, and then it has some output variables, and we write the output variables in the parentheses after the query. Note that for us, output variables may be a subset of the free variables. On our database, we allow single tuple updates, insertions, and deletions, and we accept calls to answer the query. And in the case of Boolean queries, just answers the query, and in the case of non-Boolean queries, we want to enumerate the query result. So we want a data structure that gets the domain, the schema, and the query, accepts single tuple updates to the database, and can answer the query. So how do we measure the complexity of our algorithm? Well, we use data complexity, so we assume that the query size is constant. We use the random access machine as our machine model, where we assume that we can store probabilities in constant space and that we can perform arithmetic operations on these probabilities in constant time. What we want to measure is the update time, so the time it takes to process one single tuple update, and the answer time. So for Boolean queries, the time we need to output the answer, and for non-Boolean queries, the delay, the time between two output tuples. And we begin with the problem of Boolean query evaluation. Let me first talk about the problem without updates. So for the static setting of probabilistic Boolean query evaluation, Dalby and Sushiu characterized those UCQs that are efficiently solvable and provided an algorithm for them. And this algorithm works like follows. It receives a query and a database. It applies a transformation that they call ranking to the query and the database, and then it recursively applies a set of rules to compute the probability of the query. And these rules recursively reduce the computation for some query to the computations for some smaller queries. And this gives us an inference tree, here in pink. What we show in our paper is that these rules can be made dynamic. So very briefly, step 1, we can pass updates through the ranking transformation. Step 2, in the inference tree, any single tuple update affects only a constant number of nodes. And step 3, every one of these affected nodes in the inference tree can be updated in constant time each. So in summary, we can update this computation in constant time. This gives us our theorem. So let phi be a liftable FO formula, so we can apply the rules by Dalby and Sushiu. Then for every valuation gamma of the free variables of phi, there is an algorithm that computes the probability of the query on the database under the valuation gamma and maintains this value in constant time under single tuple updates to the database. And because we can maintain it in constant time under single tuple updates, we can also do the initial computation in time linear in the size of the database. And together with the theorem by Dalby and Sushiu, the dichotomy, we get the following corollary, that every Boolean UCQ is either sharply hard or can be maintained in constant time. Now let's move on to dynamic ranked enumeration, which is the following problem. We have a non-Boolean query, so some of the free variables are designated as output variables, and the others are fixed to constants. And we write the output variables in parentheses after the query. So here the output variables are x. And the result of the query is a set of assignments to these output variables. And because we work with probabilistic databases, each of these assignments also has a probability. We want to enumerate the set of assignments ranked by their probability. So it means the most probable assignments should come first. And again, we are in a dynamic setting, so we want to allow single tuple updates to the database. And what we get is we have two modes for our algorithm. So we have the update mode where we accept updates, and we have the enumeration mode where we enumerate the result set. Okay. What we show in our work is a class of R-liftable queries. and an algorithm that can perform dynamic ranked enumeration for these R-liftable queries with logarithmic update time and logarithmic delay. Now, what are these R-liftable queries? Let me show you the recursive rules. The first rule is the base case. So when we have a non-Boolean query phi that has no output variables, then it really is just a Boolean query, and we can apply our Boolean lifting rules from before. So we define this query as R-liftable. The second rule lets us transform free variables into output variables. So when we have an R-liftable query phi with output variables x, that is R-liftable, and we have a free variable y that occurs in every atom of the query, then we define also as R-liftable the query that has as output variables both x and y. And so we can also dynamically ranked enumerate this query. And the third rule gives us conjunction and disjunction. So if we have two R-liftable queries, phi1 and phi2, and their output variable sets are disjoint, and the two queries are independent, then we can also dynamically ranked enumerate the conjunction and the disjunction of these two queries. And we also say that these two queries are R-liftable. Alright, let me briefly sketch the algorithm. I'm going to skip the Boolean rule and start directly with rule number 2. So we have an R-liftable query phi with output variables x. And now we want to show that we can add the free variable y that occurs in every atom of the query to the output variables, and that we can do dynamic ranked enumeration also for that query. And so when we map y to any constant a, we can apply our dynamic ranked enumeration algorithm to the query that has only output variables x to get child instances. Okay, we use these child instances now to create our algorithm. What we do is we keep a priority queue with one entry for every constant a that is supported by our database. And this priority queue stores for each such constant the probability of the next output tuple that the child instance for that constant has. So during update mode, this next output tuple is always the first one. So when we get an update, we propagate the update to the affected child instances, we receive the updated probability from these instances, and then we update the corresponding entries in the priority queue. And during enumeration mode, we look at the first entry in the priority queue, so let's assume it has constant b. We output the tuple of the child instance for b, and then we call next on the child instance. And last step, we update the entry in the priority queue with the probability of the new next output tuple for this instance b. Alright, because the length of the queue is bounded by the number of constants that appear in the database, updating a single entry in the queue is possible in logarithmic time. And calling next or update on the child instances is also possible in logarithmic time because the query with output variables x is R-liftable. And we only need to do this a constant number of children per call. So we get logarithmic updates and logarithmic delay for this algorithm. Okay, let's move on to rule number 3. Recall that the third rule was like this. We have two subqueries with disjoint variable sets, and their queries are independent, and we want to show that the conjunction or disjunction can also be dynamically ranked enumerated. Let's consider an example. So here we have query Rx and Sy. The two variable sets are disjoint, the two queries are independent, and both subqueries are liftable. Okay, so imagine this result set for Rx and this result set for Sy. Each of these output tuples is an assignment for the variable and a probability. Now look at the first output tuple from each, and for each such pair of output tuples, we can compute one product output tuple. So for example here, we assign x to a and y to b, and then we compute the product of the probabilities. 1 times 0.9 equals 0.9. And we can do that because the two subqueries are independent. And when we do this for all pairs of output tuples, we get some sort of Cartesian product. And this is the space of output tuples we need to output. So during update mode, what we do is we keep the first output tuple for our query. And this is the product of the first output tuples of our children. So we can do that in logarithmic time. We update our children and then we compute the product. During enumeration mode, we keep a priority queue with a set of candidates for the next output tuple. And because our subqueries, the outputs are ranked, we only need to consider a bounded number of candidates for this priority queue. And this gives us logarithmic updates and logarithmic delay. Alright, I hope this gave you some intuition for our algorithm. Let's move on to an application to non-repeating conjunctive queries. Okay, so there is a theorem by Bergholz, Keppeler, and Schweikart from POTS 2017 that non-repeating conjunctive queries on deterministic databases, if the OMV conjecture holds, then we can do dynamic ranked enumeration with constant delay and constant updates if and only if the query is Q-hierarchical, which is some syntactic property of the query. And our theorem shows that for non-repeating conjunctive queries on probabilistic databases, if the OMV conjecture holds, then we can say that we can do dynamic ranked enumeration with logarithmic delay and logarithmic updates if and only if the query is Q-hierarchical. That was the application to non-repeating conjunctive queries. We also support TopK enumeration, where the user can abort the enumeration, and open-world databases. Let's recap. We worked on tuple-independent probabilistic databases. We showed dynamic Boolean query evaluation, and we showed for non-repeating conjunctive queries a characterization of those queries that allow efficient dynamic ranked enumeration. An open problem would be to show enumeration complexity of larger query classes. Alright, that was my talk. Thank you very much for your attention.